Good morning. My name is Pierluigi Vellucci and I'm a PhD student at the University of Rome La Sapienza. This talk is devoted to a mathematical experiment about nested square roots of 2. The substances, the ingredients of this experiment are numbers, radicals of 2, and formulas. While the tools employed here are, first of all, OEIS, the online encyclopedia of integer sequences, and mathematical proof. In order to obtain the result of the talk, the mathematical proof employed here is a simple proof by mathematical induction. I now outline the talk. First step, we give some preliminary experiments. In the second step, we say about binary code, and we introduce a particular binary code, widespread in informatics, that is gray code. In third step, we show and prove the result of the talk concerning an particular ordering of the nested square roots of 2, thanks to OEIS database, this research on OEIS database, and gray code. In the fourth step, we discuss a previous reference, and in the last step, we give some conclusions and final remarks. Well, in this talk, we highlight some of connections between nested square roots of 2 that have this form, and the gray code. The nested square roots of 2 considered here are obtained from the zeros of a particular class of Chebyshev polynomials, which we called Lucas-Lehmer polynomials, for one reason, because they are created by means of the same iterative roots of a particular primality test, that is the Lucas-Lehmer primality test. The properties of these polynomials are approached in a previous paper. The experiment is structured in the following steps. We wonder what is the effect of plus sign and minus sign in the nested square roots of 2. And so on. And giving some preliminary consideration and results. Second, we apply a binary code that associates bit 0 to plus sign in the nested form, and bit 1 to minus sign in the nested form. And we give some numerically experiment for the first zeros associated to polynomial for n equal 2, n equal 3. This means that we consider LND of x for n equal 2, n equal 3, and so on, because the zeros of these polynomials are just these radicals. In the third step, we employ an internet search on OEIS database, and we search, we found the gray code in the form, in the nested form above. In the last step, we give the proof of the iterative formula. This is a joint work with Alberto Maria Berzani. Well, this is the preliminary experiments. This is a well-known formula, and we know that there are n nested radicals and n minus 1 internal signs plus signs. This is traduced in the right-hand descent in the argument of cosine function of the term n plus 1. In symbols, this means that n plus signs in the nested form is traduced to n plus 2 term in the argument of cosine. To understand what is happening by inserting a minus sign or more minus signs inside the nested radical, we consider the following example. We have these nested radicals with more plus and minus sign. Thanks to well-known formula, trigonometric formula, we have that this nested form can be rewritten in this way. But we analyze this simple result. The effect of addition of a minus sign after m plus signs is so schematized from left to right. Minus sign m plus signs is traduced in the presence in the argument of cosine function of a pi over 2 and a minus sign. Let us consider now more let us consider the following form. We have from left to right a minus sign, m2 plus sign. This means that we are considering the following nested form: 2 minus 2 plus 2 minus 2 plus and so on. This is first minus sign. This is m2 plus sign. This is another minus sign, and these are m1 plus signs. Thanks to some consideration on trigonometric expression, we have that this nested form can be rewritten in this way. This result can be generalized to a generic number k of minus signs. In this way, with this proposition, k is the number of minus signs, and we consider the more generic chain. We have first of all plus signs and so on, and we have the following generic nested form. Then this form can be rewritten in this way, in a cosine function. This is not a new result because it is a well-known result. For example, it is stated in a book on Olympiad problems and is reported in works of Timio published to the American Mathematical Monthly with this lemma. We now go to binary code section. Let us consider plus and minus signs in the generic nested form. And we apply the simple code. We associate a plus sign to 0 bit and the bit 1 to minus sign. And we rewrite in a more compact form the above nested form. In this way, we recall all in this way. Then the notation is for the following reason, because if we consider radical 2 plus radical 2 plus radical 2 and we consider all the possible choice, we have that there are four combinations, and two signs, plus plus, minus plus, and so on. Then all possible combinations are in power of 2. And we now consider a simple example. We have, with this notation, that n is equal to 3. Then we have that the biggest radicals are the radical where that has all plus sign, while the smallest radical is the radical that has only one plus sign and the minus sign in the left. This is the example for n equal 3.
The approximate value means in the limit?
Yes. And we have now n equal 4. We notice that there are two important facts. That this is still the maximum radical, and this is still the minimum radical. 1, 0, 0 is related to 1, 0 of the previous example. And this string 0, 0, 0, 0, 1, 0, 1, 1, thanks to an internet search on the OEIS database, reveals the existence of gray code in this nested form. What is the gray code? We know that the classical binary code is built in this way. When we consider step 1, we have 0 and 1. When we consider step 2, we have 0, 0, 0, 1, 1, 0, and 1, 1. When we consider step 3, we consider 0, 0, 0, and so on. We have, 1, 1, 0, and 1, 1, 1. We have 8 combinations. Then this is the classical binary code. And if we consider various steps, the binary code of order n, for example, order 3, is built in this way. 0, the binary code of order n minus 1, 1, and binary code of order n minus 1, because 0, 0, 0, 1, 1, 0, 1, 1 is just the previous step. This is also for this case. And then the generic NTH binary code is rewritten in this way. This is not the same. This is no longer true for gray code. The gray code has a different mathematical rule. It is the following. For example, we start by step 1, we have 0 and 1. Step 2, we have 0 and 1, and we complete with 0. But for the second part, we reverse this string and we write 1, 0 with 1, 1. For step 3, we have 0, 0, 0, 1, 1, 1, 1, 0, and it's just the second step. And we complete with 0, 0, 0, 0, and we reverse the previous step, 1, 0, 1, 1, 0, 1, 0, 0, and complete on ones. We have that the generic Gn, that is the gray code of order n, is built in this way: 0, 1, Gn, and we use the following notation to indicate the reverse operation on Gn. This is the gray code. It is widespread in informatics. The gray code, more formally, is a binary code of order n and length 2 in power of 2. And this is generated in this way. For a generic step, we have if this is g n minus 1, and so we have that Gn is Gn minus 1, 1, 0, 0, Gn minus 1, 1, Gn minus 1, and 1. This is the gray code of order n obtained by previous step. This is an example, and we recall that the following notation, and that we have when for a nested form of this type, 2 plus and so on, with n minus 1 signs, we associate 0, 0, and so on, 0. Then we can rewrite in this way, with this notation, 0, 0, n minus 1 times. Then this is the our notation, this form is rewritten in this way, and the same occurs for this. Well, with the following, we prove that the string which we code with 0 and 1 follow the ordering of gray code. We show a sketch of proof. The theorem says that the ordering is the following, namely that is the statement of the theorem. The proof is approved by mathematical induction, and if we consider the inductive step, we assume this hypothesis, and we prove that use the result above for gray code, because we have that gn1 gn in power of 2 is are the gray code, and we write gn1 and so on. Well, this condition is traduced in this way, thanks to a mathematical rule of gray code. Then the proof is constituted by 3 steps. In the first, we prove this inequality, and is for the first part of gray code. The second is related to the second part of gray code, and is, while the third is the inequality on the on these two strings. This is the proof of the result of the talk. In previous reference, we have, among others, the theorem of Servi that can be rewritten this nested form as a cosine function, while Niblom afterward, in a paper published in American Mathematical Monthly, write in different conditions. We have x greater of 2, that this nested form has the following formula. Conclusions. We have that the radicals considered here, the nested radicals, are obtained from the class of Lucas-Lehmer polynomials. And if we consider L1, L2, we can see that all the zeros have the form of nested radicals. And when x tends to 0, L2 of x has the following asymptotic formula, as we can see in the picture. The same occurs for L3, and these are their zeros, and the asymptotic expansion in x to 0 is the following, and the same occurs also for L4. Well, this means that at each iteration of Ln, that is minus 2, we have that all the zeros of this class of functions are the nested square roots of 2. And we have proved in this talk that the ordering of that 0 follows the gray code rule. In further papers in preparation, we are trying to apply the result obtained here in order to prove some connection on nested radicals and zeros of cosine function in the asymptotic expansion. And this can be could be allows to use the pi formula for in terms of nested radicals, because if we consider the first zeros of this term, we have the smallest zero. We have that it is and so on. We have proved that this is the smallest zero of this function. Well, this is the zero, but if we consider the previous considerations, we have that L3 is asymptotic in x tends to 0 to 2 cosine of 4x, and the same occurs for L4 when we have that Ln of x as an asymptotic expansion of in x tends to 0. But when the zeros are very close together, we have that the first zero here is here. If we consider this relation, we have a well-known formula on pi well-known pi formula, and the future aim is to obtain the formula for other zeros of cosine function, and thanks to gray code. And excuse me for my English and the thank you.